Welcome to this explainer. Today, we're diving into the absolute superhero of materials science, chromium carbide. If you've ever wondered how modern engineering survives the absolute harshest, most abrasive, and blistering environments on Earth, well, you're in the right place. We're going to unpack exactly how this incredible ceramic acts as the ultimate industrial armor.
To really grasp its raw power, just consider this extreme number, 1890 degrees Celsius. That is the exact melting point of our material. It's this staggering thermal stability that lets chromium carbide survive right inside the blistering core of jet engines, the insanely abrasive environments of coal-fired power plants, and the highly corrosive depths of petrochemical refineries, literally without breaking a sweat.
So here's our roadmap for today. We'll cover the ultimate industrial armor, inside the orthorhombic crystal, building a better cermet, the high-temperature kryptonite, and finally, the future of materials science. Let's get right into it.
Starting off with Section 1, the ultimate industrial armor. What's truly wild here is how chromium carbide vastly outperforms traditional tungsten carbide the second the heat gets turned up. Tungsten carbide is a famously tough material, but it actually oxidizes rapidly at just 550 degrees Celsius. Chromium carbide, it completely holds its own and resists oxidation all the way up to 870 degrees. And here's the kicker. Its thermal expansion coefficient perfectly matches that of steel substrates. This means that when a massive aerospace component heats up and expands, the chromium carbide coating expands right along with it. No catastrophic cracking, no flaking off, just perfect synergy.
Getting to this point took a massive evolutionary leap. It all started back in 1893 with French chemist Henri Moissan synthesizing chromium carbides in his newly invented electric arc furnace. Then we skip ahead to the first-generation cermets of the 1950s. By the 1970s, thermal spray coatings totally revolutionized how we apply this armor to giant industrial parts. And now, here in the 2020s, we are literally engineering this stuff at the atomic scale with nanostructured and high-entropy systems. It's been quite the ride.
Moving on to Section 2, inside the orthorhombic crystal.
Okay, so look under the hood, and the secret sauce is this indestructible orthorhombic scaffolding. It's categorized under the PNMA space group, if we're getting technical. Basically, this specific geometric layout locks carbon and chromium atoms into an incredibly tight covalent bond. Because these atoms are forced into this highly stable lattice, with carbon atoms tucked perfectly into octahedral interstitial sites, the material achieves extreme hardness. We're talking up to a massive 2000 on the Vickers hardness scale. But hey, every superhero has a weakness, right? For pure chromium carbide, its Achilles heel is inherent brittleness at room temperature. If you take a solid block of this pure ceramic and just strike it or put it under heavy mechanical stress, it'll shatter. Its low fracture toughness means it simply cannot be used as a standalone structural piece.
Which brings us to Section 3, building a better cermet.
Enter the cermet. This is where engineers got incredibly creative. A cermet brilliantly combines that brittle, wear-resistant ceramic armor with a flexible metallic glue, usually a tough metal binder like nickel chromium. By embedding the ultra-hard chromium carbide particles inside a ductile metal matrix, the metal actually absorbs impact energy and flexes. This prevents the ceramic from cracking, while the ceramic itself provides that ultimate, unyielding surface protection. Best of both worlds, really.
But you might be wondering, how in the world do we actually fuse these two drastically different materials together? How do you process a ceramic that melts at nearly 1900 degrees Celsius alongside a much softer metal without totally ruining the microscopic structure of both?
Well, scientists came up with a really clever solution called reactive sintering. Instead of trying to mix pre-made ceramic with metal, they mix elemental chromium, carbon, and nickel powders together. They press it into a shape and then crank the heat up to around 1200 degrees Celsius. And what happens next is just awesome. The chromium carbide is formed in situ, meaning it actually creates itself right there in place during the heating process. The liquid metal binder acts like a fast-acting glue, resulting in fine, uniform grains and a flawless, ridiculously strong bond between the ceramic and the metal.
Now, what if you need to coat a massive existing structure? Say, a giant hydropower turbine operating in a muddy, sediment-heavy river. You obviously can't stuff that into a furnace. Instead, we use high-velocity air fuel, or HVAF, thermal spraying. The big advantage here is lower temperature combustion. This is absolutely crucial because if the flame is too hot, it actually damages, decarburizes, and oxidizes the carbide before it even hits the target. HVAF keeps things just cool enough, blasting the powder at supersonic speeds to form a dense, impenetrable skin.
Now, for creating solid, standalone parts rather than just coatings, engineers turn to spark plasma sintering, or SPS. The magic here is the sheer speed of processing. SPS zaps the powder with pulse direct current, which allows for insanely rapid heating and densification. And speed matters a lot here. If you hold chromium carbide at high temperatures for too long, the crystal grains grow way too large, severely weakening the structure. SPS essentially freezes the cermet into shape before those crystals have a chance to overgrow.
Or, for some truly cutting-edge applications, we can bypass heat altogether with cold spray technology. Basically, we use a high-pressure carrier gas to accelerate solid particles to supersonic speeds. They literally smash into the substrate in a solid state, locking together through pure kinetic impact. By completely avoiding melting, we get virtually no thermal degradation, incredibly low porosity, and an absolutely flawless, oxide-free coating that keeps the original properties of the raw powder intact. It's like extreme microscopic sandblasting, but instead of wearing the surface away, it builds an armor.
All right, let's move to section 4, the high-temperature kryptonite.
Despite all these amazing fabrication tricks, extreme environments still pose an existential threat. You see, chromium carbide protects itself by forming a dense chromium oxide shield on its surface. But once operating temperatures push past 900 degrees Celsius, that protective oxide layer simply vaporizes. It just volatilizes away into thin air, entirely losing its protective effect and leaving the raw carbide completely exposed to the harsh environment.
And once that shield is gone, a completely devastating chain reaction kicks off. The exposed carbide undergoes rapid decarbonization, turning into carbon monoxide and carbon dioxide gases, which literally blows microscopic pores into the material structure. The metal binder elements diffuse and form brittle intermetallic compounds. The remaining carbide grains clump together into large, weak clusters. And to top it all off, that once tough metal binder gets soft and starts to plastically deform. This entire multi-stage breakdown can literally tear a high-performance aerospace component apart from the inside out.
Which brings us to our final section, Section 5, the future of material science. But scientists aren't letting this 900-degree limit be the end of the story. The next frontier involves ripping out that traditional nickel-chromium binder entirely and swapping it for high-entropy alloys. These are complex multi-element metals that keep their unbelievable strength and ductility even under extreme heat. We're also seeing the integration of max phases, creating composites that actually self-lubricate at high temperatures, which drops friction off a cliff. And get this, we are even using additive manufacturing, basically high-tech 3D printing with lasers, to print wildly complex, functionally graded, completely crack-free cermet components that used to be totally impossible to machine.
Which leaves us with one fascinating final thought to take away from this explainer today. As we continue to combine machine learning with atomic-scale structural manipulation, totally bypassing the historical limits of this ultimate armor, what impossible engineering feats in aerospace, nuclear power, and clean energy will chromium carbide unlock for us tomorrow? Thank you so much for joining me, and as always, keep exploring.